Hi all, welcome to part 21, module 2, logic system design. So we were discussing K-map and we saw different variations and the concept of prime implicant, essential prime implicant, and how to come up with the minimum sum of product in a unique way or more possibility, everything we explored so far. Now let's see a variation of it called, something extra we have to consider in a K-maps called don't care conditions. So what is it? So in practice, some applications the in practice in some application the function is not specified for certain combination of the input variable. So typically what we see in so far is let me take an example. Boolean expression, we can visualize it as a function. What does it mean? Yeah, one second. So what we've seen so far, suppose I have a boolean function, say f of a comma b is equal to something like say sigma of 0 comma 3. What does it mean? So typically it's a so sigma of 0 3 comma 3 means I have a min term 0. So what is min term 0? A bar b bar, right? A bar b bar, then min term 1 is also there, that is a b. It is something like a XOR b. Okay, not XOR, it is XNOR, right? So this function and all we saw already, a XNOR b, right? So that about it. Now what does it mean? So when I have a two variable a b, I have a different possibility for this a and b, that is like a 0 0 0 1 1 0 1 1. So this is my domain, right? So why I am calling it as a function, and I have a codomain containing 0 and 1, and I have a mapping like as per the definition of the function, it is given that 0 corresponding to 0 0 it is 1, because it's a min term, right? Similarly for these 1 1 also it is 1, and in these two cases it is not mentioned in the question, means they are max terms. Something like they are giving you a value of 0. So whenever I have a boolean function, something like this f of a comma b, here all possible input value is assigned to either 0 or 1, right? Either 0 or 1. So like that, 2 raised to 2 raised to 2, that many 2 raised to 16, 2 raised to 4, right? 16 such functions are possible. So here we are not worrying about something like an input combination where this function is not assuming any value. Okay. Now the thing is that sometimes there may be situation where for certain cases we know what is the output, like 0 or 1, but certain cases of the input we don't know what is this function maps to, something like this. So 0 0 0 1 1 0 1 1. Now I am thinking of a different function. Say let me take 0 1 here. Now what the function is doing, it's a different function, say f dash, that is from a to b. So here I am defining like say 0 0, let it map to this one, 0 1, let it also map to this, 1 0, say let it map to 1 1 1. I don't know, because I don't know in the sense, say let me give you, so what is an don't care, something like an input to combination is called don't care if it never occur as input to a digital circuit, or it occurs we don't care about it, something like this. I mean, so here for 1 1 I don't know what to do for the function, but this say when this a and b are given the value, say 1 1 respectively, I don't know whether this function will evaluate to 0 or 1. It is not something a valid input for me, for my application. The circuit may so typically this will be implemented by this f or f dash, we will implement using some digital circuit, and that time the circuit is expected to have a input that is 0 0 0 1 1 or 1 0. It is not expected to have 1 1. So like that anything so can happen. Something like a more realistic example, let's see. So in practice, in some application the function is not specified for certain combination of the input variable. That is what we see. So when a is equal to 1 and b is equal to 1, say we don't know what this function evaluates to. So that is what we seen in the previous example. Okay, right. So that's all. So for as an example, let's take the 4-bit binary code for the decimal digit that has 6 combinations that are not used and consequently are considered to be unspecified. So what I have is a 4-bit binary code, decimal digits, something like using 4 bits, how many combinations are possible. You can have combination like 0 0 0 0 0 0 1 right? Like that, let me write 0 0 1 0 0 0 1 1 0 1 0 0 0 1 0 1 0 1 1 0, right? 0 1 1 1. Now 1 0 0 1 0 0 1 1 0 1 0 1 0 1 1 1 1 0 0 1 1 0 1 1 1 1 0 1 1 1 1 1. So I have a 4 variable function, say the input variables like a, b, c, d, and it is something like the function is expected to, the circuit is expected to get a something like a digital a decimal value, you know, decimal value, decimal digit that varies from 0 to 1, 0 to 9, sorry, 0 to 9. So 0 to 9 are all valid according to me. So 0 to 9 are all valid. Valid in the sense when I am getting an input that is ranging from 0 to 9, I will be considering it as a valid input. That's all, valid input. And valid input, what I am going to do with valid input is a different thing. So maybe it may be checking whether the input is an even number or not, input digit is an even number or not. I am just telling you, and you know, if the least significant bit is found to be 0, it is an even number, like 0, 2, 4 and all. If the least significant bit is a 1, the circuit may be answering it as a odd number, something like that. But the circuit is expected to get an input that is ranging from 0 to 9 only. But you know, so how the circuit is, I am just giving an example. So similarly you can think of any situation. So this circuit is something like it is taking a 4 input like A, B, C, D. ABCD. More realistic example you will see when we discuss the combinational circuit design. More practical example. Here simply I am taking an example. It's not much relevant one. And when I am getting in this ABCD, this circuit is giving me say a 0. So this will give me some output, right? Say x. Let me write x is equal to 0 if input is even, something like this, and x is equal to 1 if input is odd. And input what I am expecting is some decimal digit. Okay, so that is my requirement. Decimal digit I am feeding it as circuit to this input. So this will check odd or even, something like this. That kind of a circuit I am having. Maybe simply by looking at the least significant bit, I can do this. That is a very easy process, or it can generate some parity bit, whatever it is. But the input I have a restriction that it should be anything from 0 to 9, because I am expecting a decimal digit as the input. And you know, what about these combination? These are all not the same, right? 10 and all these things are not decimal digits. So as far as my circuit is concerned, these 6 combination, they are actually invalid. Okay, invalid. Now when such an invalid, typically such an input will not be coming as input to the circuit, so that is the case. But in worst case, due to some reason I given the input as a 1010 something, then how the circuit will behave? The output is something that is not deterministic. It can be 0 or 1, because we are not caring about such an input. So this is what we call as a don't care input. So don't care about it. Okay, simply. So that is what is written there. So this can be considered as an example. The function that have a specified output for some input combination are called that have unspecified output. Sorry, the output is unspecified. So what we seen is in that 6 cases, that is from the 10 to 15, that 6 cases, the output is unspecified, right? Or we can say that such an function is incompletely specified, or the domain is not completely mapped to some element of the so actually for a function we actually need, for every element in the domain there should be a mapping. So now I can't call it as a function or a total function. Instead I can call it as a partial function. So for partial function, so by default function means total function, where for all the input combination some mapping we will expect, right? So every input in the every element of the domain there should be a mapping. That is the general definition of a function. So in general we call such a pure function as total function. So this is a variation of total function called a partial function, where for some of the element in the domain we are not expecting any mapping, something like that. So it's a kind of partial function you can visualize on the background, or it's incompletely specified. In most applications, we simply don't care what value is assumed by the function for such unspecified minterm. For this reason, we can it is compulsory to call such unspecified minterm of a function as a don't care condition. So we call it in general as a don't care condition. Fine. So to distinguish them from 1 and 0, we use a special symbol. Typically, we represent this don't care with this kind of a symbol, some into, or sometimes we will use D, don't care, or into X, something like that. We will use this. There's an into mark inside a square in the map indicates that we don't care that particular minterm. Okay, whether it is 1 or 0, we don't care. We are not expecting it as an input to the circuit. In worst case, if it is coming, I am not worrying about the output, something like that. In choosing adjacent squares to simplify the function, we will use this don't care along with the 0 and 1, and that we will see how the simplification is done with the don't cares. When simplifying the function, we can choose to include each don't care minterm with either ones or the zeros, depending on which combination gives the simplest expression. So don't care we will use only if we get a minimal expression using the function. In that case, we will assume this don't care to be 1. We will see that. Okay, so simply if you want, you can try this one also. I will be taking a different example. So in the KMF, what will happen? There are 16 entries, right? 0 to 15, and from 0 to 9 it is having the mapping like this. So for odd number, the function is giving an output to 0. So corresponding to this odd number, so how this function is evaluated, let me write it over here. The function is going to evaluate, I mean, when the input is 0 0 0 0, you know, it is odd. So this is even. For even, it is giving me 1. For odd, it is giving me 0. Okay, so again even, odd, even, odd, even, odd, even, odd, like that. Now what you will assign for the function for these inputs in the K-map or in simplification everywhere, so we can represent them with an into mark. Meaning that they are don't cares, right? So into, you can either assume it as 1 or 0, but actually it is not matters. So it's not a important thing for our circuit. We are simply ignoring such a input, right? So we are implementing our circuit irrespective of them. So but in the simplification, you may get a simplified expression if you consider this into as 1. If needed, you consider so, otherwise you consider it as zeros. That is up to your choice. That is it. So now you can visualize the K-map for the same question on the background, and you can try it yourself. Maybe something it looks like, so there will be a 4 variable K-map, right? We will see this. So that there will be 4 rows and 4 columns, 16 cells will be there totally, and what are all the input I assumed? A, B, C, D, right? So A, B, C, D, and the combination 0 0 0 1 1 0 1 1 0 0 0 1 1 0 1 1, right? So now you can fill the minterms like 0 1 2 3 4 5 6 7. Now these are all 8 9 10 11 12 13 14 15. So now you can map the value, and you know that the function for 0, it is giving you 0, right? Because 0 odd number, sorry, even number, odd number, odd number, even number, even number, odd number, odd number, even number. Now again 8 even number, 9 is an odd number, and for the remaining combination, that is 10 11 12 13 14 15, we have the don't care in the truth table. So now the truth table as well as the K-map, so that looks like this. Now how to simplify this, you know, to get the minimal expression? We will see this after seeing some more rules, and on detailed example we may come back to this. Okay, we will see that. So what you can observe further is don't care input combination. What is it? It's an input combination is called don't care if it never occur as input to a digital circuit. That is our default assumption. It is not going to come as input to any digital circuit. In worst case, if it occurs, we are not going to care about it, right? So I mean, it can be 0 or 1. It's not a big thing for us. So it is not a valid input. That's all. Now, how this don't cares will be treated by implicant, prime implicant, and essential prime implicant. So, if you don't know what is this 3 terminology, please watch the previous video where I am explaining everything in detail. What is implicant, PIV, so many examples. Okay. Now, I assume that you know what is this implicant, prime implicant, and essential prime implicant, and I am going to tell you how these things will vary when it comes to don't cares. So, implicant, you know, the basic definition of implicant, what we seen is, so we will group the ones, right? It can be a single one, right? So all combination we by default we call as implicant. So it can be 1 1 2 1 4 1 8 1 8. So there are many implicants, right? And now the don't cares are also implicants. That is the thing. You can include this don't care. You can assume the don't care to be 1, and you can make any number of implicants. So just treat the don't care as ones when you count the number of implicant. But typically this implicant, there will be a number of, it's a very big number, right? Nobody is going to ask you how many implicants are there, but they can ask you how many prime implicants are there given don't cares also. In prime implicant also, you will group one or 2 or 4 or 8 ones, and that time you group this don't cares also. Just treat the don't cares like one and group them along with the ones, and try to form the biggest group. Biggest group corresponds to the prime implicant. Hope you remember. The implicant can be of any size, but the biggest one means or the smallest product term, that is what we call as the prime implicant. And when you remove a particular variable, no longer it is going to imply your function. So that default definition we will apply, but only thing is, when you find the biggest grouping, we will consider the don't cares also. But finally when it comes to essential prime implicant, don't cares do not make a prime implicant essential. So this is very important. So we are not going to consider the don't cares when it comes to essential prime implicant. So essential prime implicant requirement, it should contain at least one that is not covered by, so that is exclusively covered by this prime implicant. And that time you purely look for one, don't look for the don't care. So don't care is not going to make a prime implicant essential. So that is a conclusion. So when a prime implicant is getting essential, when you are having at least one that is exclusively covered by this prime implicant, that is clear. That should be clear. Then only you will understand this. Now consider that default definition only. Don't consider prime don't care in place of 1. So when you find this don't care, it is exclusively by the presence of a 1, not by the presence of a that means don't care is not going to make your prime implicant essential, right? That's all. We will see examples. Okay, so this is what you are supposed to simplify. So that simplification procedure is given, but I think we will do it here. Okay, so that you can correlate things. So let me draw a small map. 16 cells are needed anyway. Okay, I'm trying to draw it here. For rows and 4 columns, the variables are like w, x, y, z. The detailed solution is given in the next slide. 0 0 0 1 1 0 1 1. Here also it is 0 0 0 1 1 0 1 1, and the numbering and all. Okay, I am comfortable with this writing the numbering, so that I can do it without any mind processing. 4 5 6 7 8 9 10 11 12 13 14 15. So now just mark the ones and don't cares. 1 3, then 7, 7. If I am making any mistake in exam also, you have to be very careful this numbering and all, otherwise you will get the wrong answer. Okay. Yeah, fine. 7 is there, then 11 is there, 15 is there. So only this many ones are there. Now what about the don't cares? Don't cares, they are giving like this. Typically they will give don't care of this variable. It's 0 2 and 5. So those inputs we are not caring. 0 is there, 2 is there, then 5 is also there, right? Now your task is to find out the prime implicant first. So first you have to find out all the prime implicant, and you know how to do the grouping. Just focus on the largest grouping. Though this corresponds to one prime implicant, right? And this corresponds to another prime implicant. I am not making it complex by writing what is the prime implicant and all in this slide. I am just marking only, and you know how to write the prime implicant corresponding to this. And this is also a prime implicant, right? So totally how many prime implicants I am getting? I am getting 3 prime implicants. Now tell me which are all essential. That is the next question. That is interesting. So what I understood is, or I think I can let me write the solution also. What I understood is, so this grouping corresponds to what? This grouping corresponds to w bar x bar. Okay, other things will vanish, and this one corresponds to what? y z, and this group corresponds to what? This group corresponds to w bar 0 to 1, y changes z, w bar z. Like that I am getting 3 different prime implicants. Okay, there are 3 prime implicant. Now the question is, so I know that all these are prime implicant. This is also prime implicant, and this is also prime implicant. Now is it essential? That is my question. And to make a prime implicant essential, I don't know, I am checking, is it essential prime implicant? So you just try yourself with your understanding and from the previous slide. So let me tell you the answer. So you can see that this one is actually, it is not a prime implicant, and this is also not a prime implicant, but this is a prime implicant. Just think of it, why I am saying like that. I will pause the video and think of it. I will tell you the reason. Okay, see why it is so. It is just like this. So why I'm calling this as a prime, this y is qualified as an essential prime implicant because of this one, because it is only covered by this particular prime implicant. This also fine. So these two things are making y is a prime essential prime implicant. And now why this what called this is why this is not a prime. You know that if I'm looking at this one, it is covered by 2 prime implicants, so this is not the correct candidate. Here also it is covered by 2 grouping, here also it is covered by 2 grouping, but this x, you know, it is covered, we feel like it is essential because of this x. But this is what I clarified in the last slide. When you count this essential prime implicant, the don't care is not going to make your prime implicant essential. So that is what we written last, right? The don't care do not make a prime implicant essential. That is very important. So because of this don't care, you can't say that it is essential. But instead of this don't care, if a 1 came here, definitely it will be a essential prime implicant, right? Hope it is clear. Now similarly the this way also, why it is not, because if I am looking at this one, it is covered by 2 grouping, this also covered by 2 grouping. These two don't care, we feel like they are actually covered by this one only, it is essential. But don't care you are not supposed to consider. Instead of that don't care, if one was there, then definitely it will be essential prime implicant. So what we concluded is there is only one essential prime implicant. There is only one essential prime implicant, and there are 3 prime implicants. So essential prime implicant is only one. Now tell me what is the minimum sum of product expression corresponding to this. And in the minimum sum of product expression, definitely you are going to write the essential prime implicant and tell me what is that y is it. So when you write this y is it, you know these two ones are covered. Now consider only those prime implicant that cover the remaining one. So you can take any number of one, but you know the requirement for minimal function, the minimized expression, we need the minimum number of term as well as the minimum number of letters per term. So always we will focus on the prime implicant that cover the remaining one with the maximum minimum number of such prime implicant and maximum size prime implicant. That is what we are focused on. Anyways, in this case only what I am interested is this particular one. That particular one is actually going to give me 2 different minimum sum of product expression. So what you can see is so this y z is definitely there. Now the next term you can consider, you can either consider this w dash z to get the minimum sum of product, or you can consider this w dash x dash. But on the other side, definitely you should consider the essential prime implicant, that is y z. So there are 2 different 2 minimal sum of product expressions are there. Okay, why you are getting 2? Because that essential prime implicant alone is not covering all the ones in your expression. So essential prime implicant you added, and the minimum prime implicant, minimum and largest size prime implicant you can add further, and there you have a choice, either that one is covered either by this w dash z, or that one is covered by w dash x dash. Okay, accordingly you are getting 2 different minimum sum of product expressions. So it is explained here clearly here. Here this is the first grouping. So if I consider if I consider that essential prime implicant y z and w dash x dash, I will get this, the first figure. You can see that this is the first solution we got. As per this, this is second solution. Anyway, this is the other solution, right? So what you considered here, this one is actually your essential prime implicant. So essential prime implicant is always there in the solution, there in all the solution. But when it comes to this one, this is just a prime implicant, but it is covering this one. That is why I taken this. So all ones are covered. Or there is another choice, that is this one. This is also a prime implicant, and this is not. This is not essential. Or let me write prime implicant, not essential, something like that. Even though it is not essential, I am taking it because I want to cover all the ones, right? And I have a choice also, either I can choose this one or this one. That is why it is not essential. Okay, fine. Yeah, that's all. So hope you are clear about the don't care condition and how to come up with the solution. And in between you can try solutions. This is a random example I taken, but somewhat meaningful, right? So how can you do this in this case? What you want is the largest grouping. So this is on largest grouping possible. Sorry, we have a 8 element grouping here. Nice, right? So if you are good in this prime implicant essential prime, you can solve any question without any confusion at all. So this is the largest one possible. Now another possibility is when you count the prime implicant, you have to consider don't cares also. So that is why I am considering this, but this is not going to come in the final minimal expression, because only don't care you don't have to cover it. But prime implicant, to count the prime implicant, I am taking that also, fine. So now another one possible is this one. Is it the case? Yeah, so I am getting 3 different prime implicant. So what I can see is this is a prime implicant, and this one corresponds to what? This corresponds to AB cancelled and C cancelled and D. So this just corresponds to D. So D is this variable D, okay? And this one corresponds to what? 1 1. So AB, right? And this grouping corresponds to this A is there, B vanishes, and C is there, AC, D vanishes, something like that. So I am getting 3 prime implicants. 3 prime implicants are there, right? But how many essential are there? You can see that this one is prime implicant and is essential prime implicant. So it is both prime implicant and essential prime implicant. This D is prime implicant as well as it is essential, okay, essential prime implicant. But if you look at this one, this AB, it is a prime implicant, right, but it is not essential. Why it is not essential? Is it cover any one that is not covered by any other prime implicant? You know, by default there is no one at all. So that criteria for essential prime implicant is at least one should be covered by it exclusively. That anyway no one is there, right? So it is not going to meet that criteria. So it is not a essential prime implicant. Okay, it is not a essential prime implicant. Now what about this? This is a prime implicant, but is it essential prime implicant? Essential prime implicant means this one again there is no one at all, right? So this is also not going to be the essential prime implicant. Now why this is getting essential? Because you know, this one is there, this one is there, all these ones are exclusively covered by it, right? So everyone is making it essential. So that's all. So altogether this D is essential, fine. That is what I was trying to say. So what about the minimum? The function f corresponds to the minimum sum of product in notation. That is nothing but so the essential prime implicant is definitely there, but you know, so it is only D, right? So D is a determining factor, something like that, right? Yeah, the function just corresponds to D. Means what? The least significant bit was my D. That D is going to determine whether it is odd or even. So I just written like the function is by default D means this is going to give me a 1 when the input is odd, right? So that is how we defined. So when the input is odd means when D is 1 the function is 1, right? Whenever the input is even, D is 0, the function is going to give you 0. So it is just D, but if I am giving an invalid input, then it may show you 1 or 0, that we are not going to care about. So that about this. So this is a unique minimum sum of product I am getting for this example. Anyway, this random example only. So this is something a valid one. Yeah, thanks for watching.